Cool. And feel free to post in the chat if anyone has any questions while we're going through this. So welcome to Lab 8. Today we're going to be covering binary trees, AVL trees, and also tree traversals. Why isn't this working? Okay. So a few quick announcements before we actually jump into the content. Project 3 is due November 15th. That is this Sunday. And we did push the deadline back just because of, obviously, the election was this week, and we're kind of just trying to make sure that everyone will be okay with, all the stress that probably was happening this week for everyone. And so your Lab 7 and the Lab 7 autograder and quiz is due this Friday. And I think this is a typo right here. It says the Lab 8 autograder and quiz is also due this Friday, but I believe it should be due next Friday on the 20th. And just someone can double check that, but whatever the date in the spec is, that is the correct date. And the handwritten problem for this lab will also be due this Friday. And so the last week's handwritten problem, the answer will be on these slides. I won't be going through them, but feel free to take a look if you do want to look at the answer for that. And if anyone does have any questions, feel free to ask me about it later after we just go to office hours. Okay, so cool. We'll start with tree traversal. So let's first start off with some tree terminology, and I think it'll be really helpful if we also just kind of go through this stuff while we are looking at it visually. So I'm just going to draw a tree right here. So first of all, the root is a node with no parents. This is the topmost node in the tree right here, so that's the root. A leaf is a node with no children, so these are pretty much the bottom nodes. These are all leaves, since those all have no children. And every node but the leaf nodes are considered internal nodes, which just means that they have children. So all of this, those are all internal nodes. And so if we take a look at this node right here, I'll color that in. The depth is the distance from the root. So this will be the depth. This has a depth of 1. Whereas the height is the distance from the node to the lowest leaf node. So here the height would be 2. And siblings are just pairs of nodes with the same parent. So pretty much every node on the same level is, oh, sorry, that's incorrect. So every pair that shares the same parent is considered a sibling. So these are siblings. These are also siblings. And these last two down here are also siblings. And so let's start off with a warm-up question really quickly. So I'm going to give everyone maybe like a minute to kind of read this and digest the question. So given a binary tree with the following declaration, how do we find the minimum depth of the binary tree? And that's basically just the depth of the shallowest leaf node. So once again, depth is the height from the root. So we just want to find the shallowest leaf node. Does anyone have kind of any idea on how to do this? You could unmute yourself or just type it in the chat. Okay, if not, that is totally okay. We can actually walk through the solution together. So this is a recursive solution to find the minimum depth, aka the shallowest leaf node. And you'll have 4 cases here. Basically, this is your base case. Obviously, with every with every recursive function, you will need a base case so you can actually stop the recursion. So here our base case is if the root is null, the node you're looking at is null, then you know you have hit the very bottom or that your tree did not exist in the first place. And in that case, you'll just return 0. If we look at this if statement right here, that just means that your left subtree is empty. So what you want to do is actually traverse the right subtree. Likewise, if your right subtree is empty, then you just want to recurse the left subtree. And we have this catch-all statement at the very bottom that's just returning the minimum of each your right and left subtrees. And the +1 is just to account for pretty much every single time you're going to go down a level. Does anyone have any questions on this? Okay, cool. And so now we'll actually talk more about tree traversals. So there are 4 types of tree traversals that we'll be talking about. There is pre-order. So in pre-order traversals, you will visit the parent, and then you will visit the left child and then the right child. In post-order, it's very similar, except you're visiting the parent last. So you will be visiting the left child, the right child, and then the parent. And then in order traversal, you visit the parent between the children. So you'll be visiting the left child, the parent, and then the right child. And a level order traversal, you will start at the root and pretty much traverse by level, starting from left to right. So if we kind of look here, for level order traversal, you start here, and this is kind of what it will actually look like. Cool. And so for the recursive tree traversals, what you'll want to do is pretty much, these are your recursive calls to traverse the left subtree, and then your recursive call to traverse the right subtree. And depending on what traversal you want to do is where you'll actually visit the head node. So if you're doing pre-order, once again, you want to visit that parent before you visit the children. For in order, you want to visit the parent between the children. And then for post-order, you'll want to visit the parent after visiting the children. And once again, like any recursive function, you do need a base case. So this first if statement right here is our base case. And so to actually be able to print out these traversals, you pretty much just need a print node function. So let's do some examples. We'll start off with pre-order. I'll give you guys maybe like a minute to kind of try to figure this out on your own, and then we'll see if anyone wants to actually share their solution. Pre-order is parent left, right. Yes, that is correct. I'll write that down here actually. So pre-order, oops, ignore that. All right, so Andrew has given us a solution. 15, 6, 4, 5, 7, 23, 71, 50. And yeah, that is correct. So let's actually go over how we got that answer. So once again, the pre-order traversal is we'll visit the parent, and then we'll visit the left, and then the right subtrees. So first, we're going to start off at the root, which is 15. Since this is pre-order, we will immediately print this. So we have 15 here. Then we will traverse left, and we will immediately print this, the 6 right here. Then we will traverse left again, and we will print the parent, which is 4. And then we'll traverse left, there's nothing there, so we'll traverse back up again, and then we'll traverse right, and we'll immediately print this. And then we'll look at the left and right again, there's nothing there, so we'll go back up to this right here. And since we've already looked at the left subtree, we'll now go right. And then we'll immediately print this parent right here, 7, oops, yikes, okay, 7. And then we'll look at the left and right of 7, there's nothing there, so we'll go back up to 15. 15, we've already looked at the left subtree, so we will now traverse right. And we will immediately print out this 23. 23, we'll look at the left, there's nothing there. So now we'll look at 23's right, and we'll immediately print out this value, which is 71. We will now traverse left from 71 and print out the number that we see, which is 50. And then from 50, we go left and right, there's nothing there. So we're going back up to the 71, we go right, there's nothing there, and so on. And so this is how you get this pre-order traversal right here. Does anyone have any questions about this problem? Okay, awesome. And so now let's take a look at post-order traversals. So once again, with post-order traversals, you will traverse the left subtree, and then you will traverse the right subtree, and then finally you will be printing the head. And so we are given the same graph. I want you guys to figure out the post-order traversal, so I'll give you guys about a minute for this again. Remember, the post-order traversal is left subtree, right subtree, and then parent. So I'll give you guys about a minute. If you guys have the answer, feel free to unmute yourself or type it in the chat. Okay, so I hope that was enough time for everyone to attempt the problem. Does anyone want to share their solution? All right, that is totally A-okay. We'll actually walk through the solution. So once again, post-order traversal is left, right, and then parent. And so we'll start off at the root again. But this time, before we print out the root, we'll actually want to traverse left. And likewise, we'd want to traverse left again. And we'll want to traverse left. There's nothing here, so we're going back up to this 4, and then we want to traverse right. We're at this 5 now, we'll want to traverse left, traverse right, there's nothing there, and then we finally print out this 5. And so we go back up to this 4. Now that we've traversed both the left and right subtrees of 4, we can print out 4. And then we'll go back up to the 6. We've traversed left for the 6, but now we need to traverse right. We'll hit the 7, and before we print this out, we want to traverse left and right. And since there's nothing there, we'll print out the 7 again. And then we'll go back up to the 6. Since we've already traversed both the left and right subtrees of 6, we can finally print out 6. And now we'll go back up to 15. Before we can print out 15, we have to visit the right subtree. So we'll traverse right from here. At 23, we have to look left, there's nothing there. And then we'll look at the right subtree where you get 71. 71, you have to go left first to this 50. And at this 50, we'll go left and right. And finally, you can print out this 50. So now we're at the 71. We'll want to traverse right. Since there's nothing there, we'll be able to print out 71. And then we go back up to this 23. Since we've already visited the left and right subtrees of 23, we can finally print out 23. And finally, we can print out the root, which is 15. And something pretty important to note is if we go back to the pre-order traversal, if we look at the solution for the pre-order traversal, we notice that the root element is actually always first in the actual traversal. Whereas in the post-order traversal, your root element will always be the last element in your traversal. And this is kind of a handy trick to know, just since if we do ask you on the exam to identify what kind of traversal you are given, you can at least immediately eliminate one or two choices just based off where you see the root. Also, if you're not talking, try to mute yourself. No worries. We'll move on to in-order traversal now. So once again, with in-order traversal, we'll be traversing the left subtree, and then we'll be visiting the parent, and then we'll take a look at the right subtree. So once again, given the same graph, I'll give you guys 1 or 2 minutes to kind of at least attempt this problem before we go over it together. And just as a reminder, in-order traversal will be left subtree, and then you'll visit the parent, and then you'll go to the right subtree. Sorry, I was muted. So someone has given us an answer in the chat. Let's take a look at it. So 4, 5, 6, 7, 15, 65, 71, 23. Okay, that's pretty close. So we'll actually go ahead and take a look at how you would go through this problem as well. So once again, like always, we are starting at 15, which is the root. Oh, I should probably write this. So once again, in order to traverse left, parent, and then right. So we'll start at the root, which is 15. We will traverse left at 6. At 6, before we do anything, any printing, we want to traverse left again. We hit 4. At 4, we want to traverse left. There's nothing there. And then we want to print out 4. And then we will traverse right. At 5, we will traverse left. There's nothing there. We will look at the parent, which is 5, and print that out. And then we'll traverse right. And then so now we'll go back, we'll trace back up to 6. Since we've already visited 6 is left subtree, we'll be able to print out 6. And then after printing out 6, we'll want to traverse right. So we're at the 7 now. At 7, we want to traverse left. There's nothing there, so we will be printing out the parent, which is 7. And then we'll want to traverse right. There's nothing there, so now we can trace back up to 15. Since we've already visited 15's left subtree, we can now print out 15. And after that, we'll want to traverse right. So now we're at 23. At 23, you want to first look at the left subtree. There's nothing there. And then now we're able to print out this 23. And then after printing out the 23 and visiting the parent node, we'll be able to traverse right. And we'll hit this 71. At 71, we'll want to traverse left, and we finally hit this 50. At 50, we'll want to traverse left. There's nothing there, so we'll go back up to this parent. We'll print out 50, and then we'll traverse right. There's nothing there, so we'll trace back up to the 71. Since we've already visited 71's left subtree, we're able to print out the parent, 71, and that is how you get the in-order traversal of the same tree. Does anyone have any questions about this one? Okay, fantastic. And so the last traversal we're talking about is a bit different. This is the level order traversal. So once again, in the level order traversal, if we're given a tree, we will start the root, and at every level, we will actually read the nodes from left to right. And okay, let me, sorry, I'm trying to find my eraser. Definitely not it. Okay, well, I can't find the eraser, but if we look at the code for the level order traversal, what will actually happen is if we have the same tree, what will happen is you'll actually create a queue right here. And pretty much what happens is, let me draw out this queue. Let me add some numbers in here actually. 2, 3, 4, 5. Okay. And so what will happen is if we trace through this code, we'll first push in the head, which is the root, so that'll be 1. And then while your queue is not empty, we'll actually pop the top and print the top. So what we printed is 1. And then what happens is you'll push in its left and right. So you'll push in both the 2 and the 3. And so while your queue is not empty again, you'll pop off the top and you'll print it 2. And what you'll do is add the 4 and the 5 since we're adding the left and right. 4 and 5. And so we go through the loop again. We pop the top and print it, which is this 3. 3 has no children, so we don't have to worry about pushing anything in. We will go through it again because the queue is still not empty. We'll pop the top and print it 4, and likewise, it'll also be the same for 5. And that's how you actually get your level order traversal. And actually, an important note to make is the level order traversal is also known as a breadth first search. So if you ever see BFS, it's basically the same thing. Okay, and now I think this one's a bit simpler, so I'll give you guys maybe like a minute for this, and hopefully someone can give us an answer in the chat. It's the same graph once again, and this time we're looking for the level order. And remember, level order, we start from the very top and we're just traversing every level left to right. Okay, cool. So let's take a look at the chat. We're given an answer: 15, 6, 23, 4, 7, 71, 5, and 50. And yes, that is correct. How we arrive at this answer is we'll start at the very top, we'll read 15, then we will go down 1 level, and we're starting from the left. So we'll get 6, we're going to the right, so we'll get 23, 15, 6, and 23. We'll go down 1 more level, start at the left, we get 4. We're gonna keep going right, we get the 7 and then the 71. And finally, we're at the last level, we're starting at the left, we get this 5, and we're ending at the right with this 50. Anyone have any questions on this problem? Okay, fantastic. So let's go through another practice problem. Given a root to a binary tree, find the level of the tree with the minimum sum, and the binary tree is not guaranteed to be complete. So the time complexity for this should be O of n, and the memory is log n average or O of n worst case. And so if we have this example tree right here, the answer is level 1. So this is level 0, level 1, level 2. And this is because the sum of level 0 is 50, the sum of level 1 is 8, and the sum of this is 117. Please don't make fun of my math skills. But yeah, so that's why the answer for this one is level 1. So I'll give everyone maybe like 3 minutes to take a look at this. And if anyone has any beginning ideas or anything, just type it in the chat and we'll go over it. What is n? N is the number of nodes in the tree. That's a good question. Okay, so I hope that was enough time for everyone to at least attempt a solution for the problem. I don't see any ideas in the chat, so I'll go ahead and go over this. Oh, just as I said that, someone use ABFS and store the minimum sum value as you traverse. Yes, that is actually very close, and there's a few minor details that we'll be going over, but yes, it is a basic idea. So like it was said in chat, we'll keep track of, there's a few variables. We'll keep track of this minimum sum here, which will actually start off as infinity. We'll also keep track of the level that we're looking at and also the level that corresponds with the minimum sum. And so similarly to the BFS, we will make a queue. We'll first push in the root. And we're doing the same thing here. While this queue is not empty, we're doing some sort of operation. And so something that's really interesting is that if we look at the queue, we'll actually be able to see how many elements are in a certain level. So for example, if I had this tree right here, and this is a 1, 2, 3, 4, 5 tree again, we have this queue. We first push in the root, right? So this will be a 1. And if we look at the size of the queue, it's 1, and this level has 1 element. And then actually what we'll do is we'll pop this 1 and push in the children. So we have this 2 and 3. So once again, at the beginning of that loop, if we look at the size of the queue again, it's 2. And so this level actually has a number of elements of 2. And so kind of that's how that works. That's really cool. So we'll be able to find out how many elements are in a certain level by just looking at the size of the queue at the beginning of the loop. And we'll initialize this level sum to 0. And so what you'll actually do is you will loop through the elements in the queue that correspond to that certain level. And what you'll do is you will pretty much, this is how you're calculating the sum for the level. And this is just pushing in the children of that level once again to just make sure that you're doing that breadth first search. And then at the very end, after this for loop, you'll just want to compare if your current level sum is less than the minimum sum that you've seen so far. You're just going to update these two variables. And then you'll increment your level so you can actually pretty much keep track of what level you are on. Does anyone have any questions on the solution? Cool. So we'll move on. Could you explain the memory used? Why is the average case O log n and why is the worst case O of n? So I believe the average case of the memory used is O log n because usually at most you'll only be storing one level in this queue. And so we consider that one level, I believe, to be O log n. But the worst case scenario, I believe, if your tree looks like this, and this is like, then I believe that at some point you'll have like all of these elements stored in your tree, and that will be O of n. Okay, so let's talk about tree reconstruction now. And I think we had a question earlier about one of the quiz questions, and I hope this will help because this is pretty similar. So given the following traversals, draw a tree that would match the traversal results. I think this is a really good question, and you actually might see some questions like this on your exam. So I'm going to give everyone maybe 3 or 4 minutes to do this one, and then we can go over it together. So the question in the chat is that the post order is saying the root is 1. That is, oops. That is correct. This is the root. Does that mean we have a stick? I believe what you're asking is like if we have one of these structures. This is a binary search tree, I believe. Actually, I think this is just a tree. Yeah, this should be just a tree. Okay, so I hope that was enough time for everyone to at least come up with a solution. We'll go over this. So as someone said in the chat earlier, and like we discussed earlier, actually, the last number in the post-order traversal will always be your root. And so we know that 1 will be the element at the very top. And so if we look at the position of the root in the in-order traversal, we can also determine that the elements, these 4 elements, on the left of the in-order traversal and on the left of the root in the in-order traversal specifically, we know that these will all be in the left subtree. And likewise, the 3 elements on the right will be to the right subtree of 1. And so let's take a look at just the left subtree now. We can actually determine what is the root of the left subtree by just looking at, once again, the post order. So if we look at the same corresponding 4 elements in the post order traversal, similarly to how the root of the entire structure was at the very end of the post order traversal, we can actually determine that the root of this left subtree will be 2 because it's the furthest to the right in the post-order traversal. And so now that we know that 2 is the element that is on the left and directly under the element 1. And so now let's do that again, actually. So if we know that 2 is the root of the left subtree, we know that the elements to the left are in its left subtree and the elements to the right are in its right subtree. So since 5 is only one number, we know that 5 will just be under 2. But 4 and 8, there are 2 numbers here, but we can do the same thing where we did with the other numbers. So we can look at which of these 2 numbers is the furthest to the right in the post order, which is 4. And so we know that the 4 will be directly under the 2, and that actually the 8 will be to the left of 4. Oh, sorry, to the right of 4. And then so now let's actually move into the right subtree of 1. And so once again, we can apply the same techniques. So looking at which 3 of these elements is most to the right in the post-order traversal, we see that the 3 is. And so that's how we know that the 3 goes directly under the 1. And then if we partition that again, we know that 6 is to the left of 3 and 7 is to the right of 3. And since there's only one element on each side, we can just directly put those in. And yeah, that is actually how you would construct a tree. Does anyone have any questions about this problem? Okay, perfect. And so now let's actually move on into a more specific type of trees. We'll be talking about binary search trees. So in a binary search tree, every node to the left has to be less than the element we're looking at, and all the nodes to the right have to be greater than or equal to the node that you're currently looking at. And the reason why we use binary search trees is so we can easily search and insert items. And that's because the insertion and the lookup times, the best case is O of 1, the worst case is O of n, but the special thing about binary search trees is that its average case is O log n. And we'll be taking a look at why the worst case and average case are what they are. So when we insert an element in a BST, what we do is we will start the root and traverse downwards based on the node's value, so comparing less than or greater than, until we actually find an empty spot to append the node. And likewise, when we are deleting the node, there are, if the node has one child, we just simply replace that node with its child. But if the node has 2 children, we'll replace it with its in order successor or the predecessor. And we'll remove the in order node from its original spot in the tree and just replace it with its child if we have one. And we'll be taking a look at this. So let's actually start with the insertion. We'll start with 3. So what happens when you try to insert a 3 into this binary search tree is you'll start off at the root. And we see that 3 is less than the root, so we know we have to traverse left. So now we're looking at this 4 right here. 3 is less than this 4, so we'll have to traverse left again. And since this 4's left spot is empty, we know that we can insert a 3 there. Likewise, if we insert a 5, we'll start at the top again. So 5 is less than 8, we'll traverse left. And 5 is actually greater than 4 in this case, so we'll traverse right. And since this right spot is empty, we know that we can just insert the 5 here. Moving on to 6. 6 is less than 8. 6 is greater than 4, so we'll traverse right. And it's also greater than 5, so we'll traverse right again. The spot here is empty, so that's how we know we can insert it there. And lastly, we'll look at this 9. 9 is actually greater than 8, so we're going to traverse right. We're going to look at this 10, and this 9 is actually less than this 10, so we'll traverse left. And this spot right here is empty, so we will go ahead and insert it right there. Does anyone have questions on this method? Cool. And so now let's look at deletion. So if we want to delete this 5, since 5 only has one child, we'll simply just replace it. So we'll just replace it with that 6. We'll look at 4 now. And since 4 has 2 children, there's actually 2 ways to do it. So we can either replace it with its in order predecessor. And I'll actually write out the in order traversal here. So one thing that's cool about the in order traversal, if you do an in order traversal on a binary tree, it will actually return to you like the elements in order. But this is only on binary trees, binary search trees. It can't be on any tree. And so the in order predecessor here will just be the number that's less than 4, like immediately less than 4. So this will actually be 3. And the successor will be 6. And so if we want to delete 4 using the in order predecessor, we'll simply just swap these 2 elements and delete the 4. And likewise, we'll just be swapping these and deleting the 4 as well. Now let's take a look at 8. So 8 is actually the root. And once again, we'll be looking at the in order predecessor, which is a number that's less than 8. That's immediately less than 8 pretty much. I'll actually write out the in order. So the in order would be like 3, 6, 8, 9, 10, and 11. So when I mean immediately less than, I just mean if we're looking at 8, we're looking at the one that's immediately less than 8. And so the in order predecessor here is 6. The in order successor here will be 9. And what we'll be doing is we just swap these and then delete the 8. And now finally, let's look at deleting the number 11. And since 11 has no children, we can actually just simply delete it. And that's it. Does anyone have any questions regarding deletion in binary search trees? Okay, perfect. So what does it mean for a tree to be balanced or unbalanced? Basically, for every node, the heights of the children of K must differ by at most 1. And if this is the case, then the insert and search complexities will always be O log n, worst case. And pretty much what happens when we say the worst case is O of n is you get something that looks like this. That will provide you with the worst case complexity O of n for inserting and searching. And so now let's actually talk about AVL trees. So AVL trees are pretty much the solution to this idea of balancing a BST. So your insertion and deletion will always be O of log n. And the invariants of an AVL tree are very similar to the BST. The value of a node has to be greater than all of its values on the left and has to be less than or equal to all the values on the right. But it also has an extra invariant that the balance factor of each node must be 1 to -1 inclusive. And this balance factor is actually just the height of the left subtree minus the height of the right subtree. And remember, height is the distance to the lowest leaf node. And it's important to note that it maintains balance after each insertion and deletion. And we'll take a look at this. So similarly, inserting on an AVL tree, you just insert it in its appropriate location. But then after that, you'll have to see if you need to rotate these nodes. And deletion, similarly, you just delete it, and then you'll have to see if you need to rearrange the tree. And we'll take a look at this. So the left subtree causes an imbalance, and the left side of the subtree has an extra node. So if we look at this, right, the last element we inserted was this 1 right here. And so if we look at the balance factor once again, so remember the balance factor is the height of the left subtree minus the height of the right. So this is balanced because its balance factor is actually 0. There's nothing on the left and there's nothing on the right. We'll traverse up. The balance factor of this is 1 minus 0 since it has something on the left, but it doesn't have anything on the right. So we want to make this a positive 1. That's the balance factor. And then we look at this 3 right here, right? The balance factor of this 3 will actually be plus 2 because it has 2 elements on the left subtree and nothing on the right subtree. And so since this 3 does not actually, it is not considered balanced because its balance factor is not within the range of -1 and 1, we know we need to pretty much fix this in some sort of way to make it balanced again. And how we'll actually do this is you will rotate it right. So what will happen is that this 3 will become a child of this 2 right here, and this 2 right here will become the parent of everything. Similarly, if we have an imbalance on the right side, so we'll look at this. The last element we inserted was a 5. So the 5 has a balance factor of 0 since there's nothing on the left and there's nothing on the right. 4, if we look at the one above, 4 has a balance factor of -1 since there is nothing on the left side and there's 1 element on the right side. So you'll do 0 minus 1. And then we traverse up again. We look at this 3 right here. 3 has a balance factor of -2 since there is nothing on its left side. So we're doing 0 minus 2 because there's 2 elements on its right side. And since -2 is not within the range of -1 to 1, we know that this is imbalance. And since this is imbalance on the right side, we'll actually rotate left. And so what will happen here pretty much is that your 4 will become the parent and the 3 and 5 will become the children. So now let's look at some more complicated cases of unbalance. So the last element we inserted was actually this 2. So if we look at this 2, the 2 has a balance factor of 0 once again. And if we go up to this 1 has a balance factor of -1 because there's nothing on the left side, but we have one element on the right side. And if we traverse up, we find that 3 has a balance factor of +2 because there's 2 elements in its left subtree and 0 in its right. But since we have this mismatch of signs, we can't just rotate it one way. What you'll actually do is, since this is negative, you want to rotate that left. And then since that is positive, you want to rotate right. Now let's look at a similar problem once again. So the last thing we inserted was a 4. 4 has a balance factor of 0. 5 has a balance factor of 1 because there's one thing in its left subtree. And then 3 has a balance factor of -2 because it has nothing in its left subtree. And then it has 2 elements in its right subtree. And so once again, what you need to do here is you first need to take care of this +1. You'll want to rotate it right. And then you'll take care of this -2 right here. You'll rotate it left. And so now let's look at a really complicated example. The last thing we inserted was a 6 right here. 6 has a balance factor of 0. 5 has a balance factor of -1. And then we go up to this 4. This 4 has a balance factor of also -1 since we have this 1 minus 2. And then finally, 2 has a balance factor of -2 since we're subtracting 1 and 3. And so what you're going to do here is, since these are both negative numbers, this 2 and the -1, you want to rotate left. But it is a bit trickier here since although this becomes a root, this also has a left child. And what actually happens is that 4 will take the former root as its child, so the node that drops down, and then the node that drops down gets 4's old child. Does that make sense to everyone? Does anyone have questions? Okay, cool. And this is pretty much just showing the process. Okay, so now let's step into this practice problem. Important note, we use the in-order successor. And I'll give you guys maybe 3 or 4 minutes for this question. And then we will go over it. Okay, so let's go ahead and go over this question. I hope that was enough time. So okay, yeah. So we're first going to delete node 5, and then we're going to delete node 7. We want to know what the resulting tree looks like, and we're always using the in order successor. So I think something that might be a little handy first off is just write the in order traversal. So we're going to write IT stands for in order traversal. So this is 1, 2, 3, 4, 5, 6, 7, 8. So we're deleting node 5. We know its in order successor is actually 6. And so what we'll do is we'll actually just swap these two and then delete 5. So the resulting tree will be 6, 3, 7, 1, 4, 2, and this is 8 now, since we've removed the 6. And if we take a look at this, we notice that the tree actually is still balanced, so we don't need to do any rotations. And then now we are going to delete 7. So what this resulting tree will look like, since there's only one child, is 6, 3, 1, 4, 2, and we'll get 8. And so what we actually notice here is that this tree is now imbalanced because this root node right here has a balance factor of +2. And if we look at the one directly below it, this one has a balance factor of +1, since we're just doing 2 minus 1. And since these are both positive numbers, we just know that we have to rotate it right. And what will happen is 3 will become the new root. We get 1, 2, and 6 becomes 3's new child. And 3's old child will simply just become the root's child. So this is what our resulting tree looks like. So 3, 1, 6, 2, 4, 8. Does anyone have any questions about this problem? Okay, awesome. And so that's actually the end of lab. The handwritten problem is given here, but honestly, I'll stop the recording here.